The next section we're going to be covering is atomic subshell energies and electron assignments. So here we go. The goals of this particular section or subsection are to write the electron configurations for atoms, recognize that electrons are assigned to the subshells of an atom in order of increasing energy. Another way to say that is you assign electrons to more stable orbitals than less stable orbitals, or more stable subshells than less stable subshells. In the hydrogen atom, the energies increase with increasing n, but in many electron atom, the energies depend on both n and L. So both the principal quantum number, or shell, and the angular momentum quantum number, or the subshell. Understand the concept of effective nuclear charge, which is called Z star. Remember, the Z symbol stands for atomic number. An atomic number is the number of electrons in the nucleus. So that would be the nuclear charge. Well, we have something called the effective nuclear charge, and we'll get into that in a bit. And apply Z star in determining orbital energy levels in atoms. You may recall that we don't have a good reason for saying why an S subshell in a shell, an S subshell, is more stable than a P, which is more stable than a D and more stable than an F. And that's where Z star, or the effective nuclear charge, comes into play. All right, so let's look at atomic subshell energies and electron assignments. So we already know that for shell stability, the smaller the number, the more stable the shell. So if n equal 1, that's an electron that's more stable than in an n equal 2. And that has to do with the proximity of the electron to the nucleus. The more close it is to the nucleus, the more stable it is. All right, now for subshell stability, you've already been told that an NS is more stable than an NP, is more stable than an ND, is more stable than an NP. And remember, N refers to the shell. So in some cases, this is not a complete thing. It's too complete, if you will. For instance, in the first shell, there's only a 1s. So you can't say a 1s is more stable than a 1p because there's no such thing as a 1p. We actually have to go to the fourth shell where we have all four of these subshells. Just a quick reminder, for the first four shells, the number of subshells in that shell is the shell number. So shell 1 has 1 subshell, shell 2 has 2 subshells, shell 3 has 3 subshells, shell 4 has 4 subshells. So that's kind of a neat thing to remember. So you have to go to the fourth shell where we actually have a 4s is more stable than a 4p, more stable than a 4d, and more stable than a 4p. This shouldn't be P, this should be 4F. So I'm glad I can make that correction. So when we look at subshell stability, where we're mixing orbits, I should say shells and subshells, you can see the 1s are more stable than the 2s, the 2s are more stable than the 3s, and the 3s are more stable than the 4s. So it goes 1s, 2s, 2p, 3s, 3p, 3d, 4s. So that's the stability. I don't have room to continue this anymore, but it would be 4p, 4d, 4f, then we go to 5. So that's the subshell stability. Now, when you get to these larger shells, there's a little bit of overlap there between those energies. They get a lot closer together. And you found that when you did the lab with the hydrogen atom, where you found that the energies get really close together for large shells. So, sometimes it may be okay for an electron to be not where we quite expect it. Okay, we find that energies of shells get closer together for n as n gets larger. So this is what I was just talking about. And so there's some overlap that occurs. So we have a model for predicting the electron configuration that is not based completely on subshell stability, but it's based on what we find experimentally. So ultimately, we have an idea of what subshell is more stable than the others, but the electron filling, the model for filling them, doesn't quite follow the model for stability. Okay, So you might say, well, what are you talking about filling the subshells? And the idea is here that if we have a particular atom and we want to know where the electrons are where they are. We have to decide, well, based on the atom, where do we think they are? And then we compare that experimentally. Uh, and so when we think about where we think they are, we fill them into the shells and subshells by putting them into the more stable ones first and then moving along. So that's why we call it a filling orders, because we're manually thinking, oh, this is where this first one goes. This is where the second one goes. So right now we're going to talk about the effective nuclear charge, or Z star. This gives you an explanation for why a 2p is less stable than a 2s. And it goes on that way. So when you talk about stability, a S is more stable than a P, is more stable than a D, is more stable than an F in the same shell. So this is the explanation for why you have the different stabilities. So Z effective is the charge felt on an electron when screening and penetration is balanced. And so what is screening and penetration? I have a little drawing right here. And this here is an atom with 3 protons. So this is lithium. And for lithium, we have 2 electrons in the first shell, the S subshell and an S orbital. So these 2 electrons are pretty close to the nucleus. Then you have a third electron, because this is going to have a 3 electron system with 3 protons to be neutral. You have 3 electrons. Since the first shell is filled, the second or third electron goes into the second shell, which is going to be farther away from the nucleus on average. So this electron, when it looks at that nucleus, it actually gets screened from the nucleus by these 2 electrons. And the effect is that this electron sees a +3 and a -2 combined together. +3 minus 2 is +1. So when the electron's way out here and it looks towards the nucleus, it sees a +1 charge. Now, if you remember from the electron density map, or the radial distribution, I'm going to draw the radial distribution here very roughly. Here was the 1s, and here was the 2s. You'll notice that the 2s electron right here can be inside of where the 1s electrons are sometimes. Not often, but sometimes. So this electron, which is out here, can be right in here in front of the 2 electrons in the n=1 shell. Now that electron, when it looks at the nucleus, it sees a +1 charge. So that's called penetration, because that electron is penetrating the screening of the first shell electrons. It's getting, closer to the stage, as it were. So some of the times the n=2 electron sees a +1 charge because it's so far away that the charges of the inner electrons and the charge of the protons add together to a +1. Sometimes it sees a +3 because it can penetrate the screening of those n=1 electrons. And so you kind of have an averaging between the two, but it's a weighted average. Since the electron by far is outside of the screening, the +1 is going to have a greater influence on the overall effective nuclear charge. And so it turns out that when you actually look at the effective nuclear charge on this electron, instead of seeing a +3, the effective nuclear charge is something like a 1.3-ish, which is closer to 1 than it is to 3. So it turns out that when you look at a 2s versus a 2p electron, a 2p electron does not penetrate as well. So in a case where you're looking at a 2s versus a 2p, for instance, like in, let's see, what's after lithium? Beryllium. So a 4 electron system like beryllium, instead of the effective nuclear charge being something like a 1.2 or something like that, well, shoot, let me just show you the numbers. The 2p electron will fill a smaller effective nuclear charge. Now, the deal with the effective nuclear charge is that the larger the effective nuclear charge, the more stable the electron. So here, if we take a look at some numbers here, you can see that for boron, when you look at a 2s versus a 2p, the 2s has an effective nuclear charge of 2.58, which makes the 2s electron more stable than a 2p. And that continues for carbon. Notice that the carbon, the Z star, Z effective for a 2s is larger than for a 2p. And that continues all the way for all of these other atoms. Now, notably, it does get to be a smaller difference when you get to these larger atoms. So, when we talk about the 2s being more stable than the 2p for those atoms, it's slightly more stable, but it's important. It's important to know. So if you want to know, well, why are the subshell energies different? And the answer is because of effective nuclear charge, which is brought about from two factors, screening and penetration. Okay, so that's why when we go back to the notes and I say that a 4p or a 4s is more stable than a 4p, is more stable than a 4d, is more stable than a 4f, that's the reason why we have those differences, effective nuclear charge. Okay, so let's look at subshell energies and electron assignments. So we're still staying on this topic of effective nuclear charge. A lot of people just call this Z star. It's the net force of attraction experienced by the outermost electron in an atom. And here, this is an actual problem that we're trying to do. Which of the following statements best describes how Z star varies among the elements in the second period, lithium to fluorine? Well, we can answer this just by looking at that chart again. So they're talking about the effective nuclear charge for a particular subshell for these atoms. So we might be looking at the 2s subshell or 2p or whatnot. So let's take a look here. From lithium to fluorine, look at the effective nuclear charge as we go from lithium to fluorine just for the 2s. What happens to the numbers? Well, they get larger. And ultimately, why does the effective nuclear charge increase? And the answer is because the nuclear charge increases. So it's the same type of trend. And it's the same for the 2p. Notice that the effective nuclear charge increases because the nuclear charge increases. So the answer to our question here is which best describes there's a regular increase from lithium to fluorine. Okay. And here it says general increase from lithium to fluorine, but with exceptions. No, there aren't any exceptions. Let's look at this next problem. List the first five. The book has orbitals in order of filling according to the Aufbau principle. What they really mean is, what are the first five subshells? So when we want to take a look at the first five subshells, we know that the n equal 1, there's a 1s subshell. For the n equal 2, there's a 2s subshell, and there's a 2p subshell. For the n equal 3, there's a 3s and a 3p and a 3d. So what order do we put these in first? We do it first by shell. So we're going to go with the 1s first. The next shell is a 2. So which do we put first, a 2s or a 2p? We put a 2s because the 2s subshell is more stable than a 2p. So we put a 2p. And then finally, we go to the third shell, and we're going to put a 3s and then a 3p. And we're done because they ask, what are the first five? Oh, and I put a little 2 here. I shouldn't have put that. These are the subshells in order of stability. So when we're putting electrons and putting them into this atom, we ask ourselves a few questions. Now, I'm going to put down here a little thing here that says max. The maximum number of electrons in each of these is different. I'm also going to put this little orbitals. So in the 1s subshell, there's one orbital. In the 2s, there's one orbital. In the 2p, there's 3 orbitals. In the 3s, there's 1 orbital. And in the 3p, there's 3 orbitals. And that's an important thing to remember. When you look at the subshell type, and you look at the number of subshell or number of orbitals, this is an important table to know. It goes 1, 3, 5, 7. You'll notice it's basically odd numbers. And that's because that when you look at these number of orbitals, what are the m's of L's that you can have for each of these? Here you can have a 0. Here you can have a 0 plus 1 or minus 1. Here you can have a -2, -1, 0, plus 1, plus 2. So 5 different numbers means 5 orbitals. And for the F, you're looking at a +3, +2, +1, 0, -1, -2, -3. You'll notice it doesn't really matter what order I put them in, pluses or minuses. The fact is there are 7 numbers here which represent 7 orbitals. 5 numbers here which represent 5 orbitals, 3 numbers here which represent 3 orbitals, and 1 number here which represents 1 orbital. So that's how I get here for a 2s, there's 1 orbital. It doesn't matter whether it's a 1s, 2s, 3s. If it's an s, 1 orbital. If it's a p, 3 orbitals, regardless whether it's a 2p, 3p, or 100p, 3 orbitals. Okay, so what's the maximum number of electrons? Now remember, for an orbital, you could have an m sub s of +1/2 or -1/2, so that's 2 electrons. So you can put 2 electrons in that orbital. So what's the maximum number of electrons? 2. Here, 2. Here, 6, because with 3 orbitals, 2 electrons each, that's 6 maximum, 2, and 6. So if each of these subshells were full, it would be 1s2, 2s2, 2p6, 3s2, and 3p6, and each of these subshells is full. Now, what atom has that electron configuration? Well, here, this is the shell, this is the subshell, and this is electrons. Well, if we want to know what atom this is, just count up electrons, because however many electrons it has, that's how many protons it has. And if we know how many protons it has, we know what atom it is, or element, I should say. So here we add these up, you get 10 for the first 3, plus here you get 18, so you've got 18 electrons, therefore 18 protons. Therefore, when we look at the periodic table, argon has 18 protons, therefore it's argon because argon has an 18 at the top. So what's really neat about these electron configurations, if you can count electrons, you know what element it is. Okay, so that's the first 5 subshells going from lowest, how do we say this? Most stable, so they say lowest energy, to highest energy. Okay, so let's put that off to the side. All right, so here, going back to the subshell filling order, one way that they like to tell you about this in the book is that you can actually figure it out by looking at N and L, the principal quantum number and the orbital angular momentum quantum number. And basically the subshell filling order goes by the lowest total when you total the numbers assigned to these particular principal quantum numbers, or principal and angular momentum quantum number. So here, if you have a 1s, remember s's have a value of 0, so 1 plus 0 is 1, 2 plus 0 is 2, 3 plus 0 is 3, 4 plus 0 is 4, 5 plus 0 is 5. Remember, for p's are L equal to 1, so 2 plus 1 is 3, 3 plus 1 is 4, 4 plus 1 is 5. And for d's, the value is 2, so 3 plus 2 is 5, 4 plus 2 is 6. And the filling order goes from lower total to higher total. What happens if you have a tie? The more stable subshell is the one with a lower quantum number, principal quantum number. Okay, so this is the subshell filling order, and you fill by lower order, a lower total n plus 1. And if the tie goes to the lower n first. And here, this shows you that chart that I was showing you before, where if you look at the subshell type, the number of orbitals in the subshell type, you can also figure out the maximum number of electrons in the subshell. Now, an interesting thing here is this number here, 2, 6, 10, and 14. These are really important numbers. I'm going to draw the periodic table very quickly here. So here's the periodic table. It turns out that this part of the periodic table is 2 elements wide. This part of the periodic table is 6 elements wide, 2 and 6. This part is 10 wide, and this part is 14 wide. So it turns out that these 2 columns actually represent something about an S subshell. These 6 columns represent P subshells, and these 10 columns represent D subshells, and this 14 represents F subshells. So when we look at the subshell filling order, this is what I actually like to use. I like to use the periodic table. So we have what are called blocks. So I already told you before that with this being 2 wide, this is an S block. Now it turns out that this guy here, this little element here is part of the S block, but it just happens to be over here. These columns that are 6 wide are the P block. These columns that are 10 wide are the D block, and these columns that are 14 wide are called the F block. Now, when you number these blocks, each period is a different subshell. So when you look at the S block, the very first subshell at the top is the 1s, then the 2s, then the 3s, then the 4s, 5s, 6s, 7s. So it goes in nice order. And you'll notice that the 2p the P block starts with a 2p because there's no such thing as a 1p. So you have to start with a 2p, 3p, 4p, 5p, 6p, 7p. It's the same with the D block. There is no 1d, there is no 2d, so you start with 3d. And this is okay so far, because when you take a look at, actually, I have this shifted too far. I need to get rid of this and get rid of this. And so I'm actually going to white this out. And I'm going to white this out and this out and this out and this out, because I didn't draw my periodic table very well. So you get to see me fixing this in real time. So here, this is actually 3D, 4D, 5D, and 6D. Okay, so if you take a look at the periodic table, I call this a tower, I call this a tower, I call this the moat, and I call this the wall. The wall is down here and it starts in the 4th period. So this can be a little confusing for people, because when they start labeling these different subshells, it's naturally to start with 1. Okay, and it's not natural to start with a 2. But here you can justify by saying, hey, it's in the 2nd period, so it's a 2p. But when you get to here, that starts with a 3d when it starts in the 4th period. So that's something you have to adjust to. But the way I like to remember the blocks is this way. You start numbering each block with a different numbering. So here in the S block, you start with a 1. The P block, 2. The D block, 3. And the F block, 4. It's as easy as 1, 2, 3, 4. So this is what I like to use for getting the electron configuration of atoms and, and as a starting point for filling the subshells based on this. So we're going to take a look at this again in a bit. Now, we're going to actually take a look at this and we're going to see how to use this to get the electron configuration of atoms. And that's the end of this section. The next section will be the electron configuration of atoms, where we actually use this and get the electron configuration of atoms.